All right, so I'm going to walk us through how to do a reaction like this, all right? I feel like this is a very misunderstood concept, and I feel like it's been just kind of explained poorly in the book, so I just wanted to go from here. All right, what are we looking at? Okay, the way that this was set up on our quiz doesn't even say substitution, elimination, whatever. It doesn't matter. This is a Diels-Alder reaction. Okay. This is the Diels-Alder reaction. And it's technically an addition reaction. Okay. We need to know a couple of things. We've gone through this before, but we don't actually talk about what actually happens. Okay, you need two parts of a Diels-Alder reaction. You need a conjugated diene, and a dienophile. Well, what the heck does that mean? Well, we know what a conjugated diene is, right? It's when you have a double bond with space in the middle so that you can have some resonance, okay? A dienophile is a carbon double bond. That's it. It's just a compound with a carbon double bond, okay? That's it. Now, you can make this better by introducing electron withdrawing groups like this oxygen, okay? Here's the other thing. So let's recap here. The other thing you want to keep in mind is that you want, if possible, for your conjugated diene to develop a negative charge, and you want your dienophile to develop a positive charge, okay? So we have our conjugated diene, and if we can get a negative charge, we can. And even more specifically, it's going to connect to the positive charge of a dienophile. That's going to become important here, okay? Here's the other thing. Here's the huge thing that I feel like wasn't mentioned. This type of Diels-Alder reaction that I'm about to do only occurs when you have two unsymmetrical or asymmetric reactants, okay? Because if you have, this is like your classic Diels-Alder reaction. This is like the most simple one, okay? What's this, acetylene and this conjugated diene over here? That is going to equal, I'm sorry, these are hydrogens. What will result from this is simply that, okay? That's the simplest form of a Diels-Alder reaction. Okay. But this one, because they're asymmetric, we get two products. And we have to make a decision, what is going to be the major product? When there's two asymmetric reactants, we have two products, and we need to look at resonance and charge. Okay? The other thing, we will always get a cyclic compound. And here's the other thing, you will always have a double bond between the 2 and the 3 of your conjugated system. That is such an incredible shortcut. It doesn't matter where you name it. Let's name it 1, 2, 3, 4. Our final product is going to have a double bond here. In fact, you can already start drawing your answer. My answer is going to look like this. and keep this oxygen right where it is. That's half of my answer. That is half of my answer. In fact, because generally we know we're going to make a ring, and the most common ring is a six-sided ring, we can even make an assumption that our product is going to look like that too, without even going through anything, without even thinking about this. We already have most of our answer already done, okay? All right. But let's work through this a little bit so that you understand what is happening, okay? So because these are two asymmetric reactants, let's say we don't change anything, okay? Let's say we don't change anything. We have our original diene. And we have our nucleophile. It's like, hey, what's going on? And it's approaching. Okay. What I like to look at here, and the way you can visualize this, is that I like to visualize these three. I'm just redrawing this. Is that these three all get together and they're like, guys, can we all just rotate everybody one to the left and make a full ring? And they're like, that's a great idea, let's do that. And that's exactly what they do. Look how cool this is, right? This guy, let's go, it doesn't matter, clockwise or counterclockwise, let's go counterclockwise. This guy is gonna sit right there. This guy, unfortunately, has to stay as a double bond and is going to sit right here. And this guy is going to follow and fit here. So they all come in agreement, and they're like, let's make a ring. This is Diels-Alder. This is the heart of what happens here. Is as this double bond approaches, this is what's happening. And the cool thing is, let's say, I don't know, there was like an ethyl group attached here. It stays there. It's gonna stay there. But here's the deal. No pun intended. What if I just rotated this? What if I was approaching this way? This is the same compound, it's just rotated. Oh, well, I could also put the ethyl group down here too. Well, how do I know which? That's why, because well, in this case, it would be an identical compound just because this is asymmetrical. This is symmetrical. So I'd have to introduce like a methyl group or something here. And then you'd have that decision of like, oh, well, do I come in from the top or do I come in from the bottom? Which way do I approach? That's where we're going to get a little involved here. But just understanding how this ring forms is like the coolest thing to understand. And look, check this out. You can do the same thing with a triple bond. Let's say a triple bond comes in here. It doesn't matter. The red lines will do their thing, and this will just remain a double bond, right? If there was something attached to this, it would still be attached to it. That's Diels-Alder, okay? All right, so now that we understand how these rings are formed, I'm going to apply what we just did right here. Look, here's our double bond approaching. So here's our friends, and they're all going to do their thing. So let's form. And I'm sorry, this is what makes it complicated, this methyl oxide here. That's what makes it unsymmetrical, and that's what makes this a difficult problem, okay? All right, so okay, So we're going to do our ring around the rosy. Our double bond approaches. I'm not even going to put the other molecule in right. Well, yeah, I'm not even going to put the molecule in right now. Let's make our ring, okay? Everybody is going to, all the inside guys, let's make this even clearer. All of our inside guys are just going to rotate one. He's going to go there. He's going to go here. He's going to go here. All right, let's just erase. And what are they going to form? I'm sorry I don't make my rings attached. They're going to form this. I know that's not a pretty hexagon. Let's bring this a little closer. Okay, that's what they're going to form. All right, now this is where that double bond originally was, so I'm going to just attach my dienophile right there. That's one possible answer for this, okay? But remember what we just talked about. You know, this little ketone drawn is just kind of floating in space. It doesn't, just because I drew it that way doesn't mean it can approach like that. It can also, I'll even draw it from the very beginning. Okay, that's our original product. Here comes, and I'm going to reverse it. It's this, it's this, it's this, right? It can also come in from this direction. It's going to be on, oh, you know what, yeah. It can also come in from this direction. And remember, the double bond has to kind of come in first, okay? So remember, our three red guys are going to play ring around the rosy and form one here, form one here, form one here, and this bond I'm just going to move over and fits in here, okay? Those are the two possible products, A and B, of this problem, okay? I'm sorry, I forgot to put the double bond in on this guy over here with the ring around the rosy. Those are our two possible products, and one of these is the answer, okay? The answer is actually the one on the right. Let me just confirm that. Yeah, the answer is the one on the right. But why? Why? This is where it gets a little complicated. But this at least gets you to the point where you can understand what the products are. Now we just need to figure out what the major products are, okay? All right. This is where it gets a little crazy. So let's go back and look at our starting products here. Okay, so can we change these compounds using resonance? Yes, we can. Yes, we can. And we can do that in a couple of ways. Remember, oxygen has lone pairs. It likes to be 6, 5, 4, 3, 2, 1, 0. So that's a neutral charge. This one has 6, 5, 4, 3, 2, 1, 0. Okay. Whenever you see a double bond in a conjugated system like this, we know that a double bond can move to oxygen. Remember, oxygen is electron withdrawing. It's going to pull electrons towards it. And this is going to resonate, and that's going to follow suit, okay? So what is that going to look like? Well, it's going to look like this. So this has an extra set, not an extra set, but 6, 5, 4, 3, 2, 1, 0, -1. This now has a -1 charge. But we removed an electron from something. We moved an electron from this carbon. And don't forget that this carbon, even though we didn't draw it, this is an alkene, is attached to 2 hydrogens. But now it's only attached to 3 things, and it likes to be connected to 4, 3, 2, 1. This has a plus charge. And remember, we want our DNophile to have a positive charge, to be an electrophile. So this is great for us. What does this tell us? This tells us that when we approach, when we come into our conjugated diene, this carbon is going to be the one that comes in, okay? But it'd be great to have a negative charge to connect to. So let's look at this. Can we make a negative charge here? All right, well, what's happening? We have, see, this is where it gets confusing. Oxygen is electron withdrawing, but it doesn't have a pi bond right next to it that is able to withdraw. It can't withdraw anything. So what's going to give? It is going to give one of these pairs here, okay, and then the adjacent pi bond, which is this, is going to hop here. So what is that final product going to look like? Well, let's do this, 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 this. 6, 5, 4, 3, 2, 1. We just created a positive charge here. Now, don't be tempted to play around with this and move this. That's not moving. That's not doing anything. And remember, this was attached to 2 hydrogens, but now what does it have? Now it has a lone pair. Okay, 4, 3, 2, 1, 0. This has a negative charge. Perfect. This is what we want, okay? So now we just need to connect positive to negative, okay? But don't forget what I told you at the beginning. Remember when I already had half of our product already drawn? Let's get back to that. Let's make it easy for ourselves. Remember, our final product is going to have a double bond between the 2 and the 3. So let's draw that. Our methoxide. And remember, methoxide can be drawn many different ways, just as that, or as this, or as this, okay? They're all the same thing. Okay, so that's what our product is going to look like. And remember what I said before, it's likely this is going to form a 6-sided ring, because as we bring in our double bond, it's likely that this is going to form a 6-sided ring. And we already know that because this initially was the double bond of our product, and we know it's either going to come off here or going to come off here, that is where we're going to bring this in, right? Okay, so do we come in from the top or do we come in from the bottom? Well, remember, our conjugated system is still here. 1, 2, 3, 4. 1, 2, 3, 4. Our conjugated system is still here, okay? And our negative charge was on 1. Our negative charge is on 1. That's where we want to bring our positive charge to. That's where we want to bring our positive charge to. But think about this. Think about this. I'm going to draw this a little simpler because you're like, oh, okay, well, if I have a negative charge up here, well, I'm going to attach here. But think about this. Even though I drew this, we're not quite at the woods yet. even though we know it's going to look like that. That's our negative charge. I can't just bring in my little charged guy here. I'm just going to redraw this. Right? This is this resonance contributor that we're bringing in. I can't just bring him in and attach him here. That's not a ring, right? We're not forming a ring here. This is some crazy thing. That's just not going to work. This needs to rotate itself. This needs to rotate itself for this to happen, okay? So we know it's not going to be pointing up like this. It's going to, I don't know if I can. Right? It's most likely going to come in kind of this way, right? But I'm going to mirror image that. And I know this is like really advanced, but I'm going to mirror image that. Like this, okay? And there was a positive charge here. So now we're talking, because this is going to come in like this. And look at where our oxygen is kind of pointing, okay? And here's the other cool thing. We can kind of reverse our charges here and kind of make this whole again. This is negative. All right, remember our initial double bond, well, we had two initial double bonds. Let's put our lone pair from our oxygen back where we brought it. Let's put the lone pair here, the pi electron here, all right? So let's neutralize that. I lost a methyl group in there somewhere. There's supposed to be a methyl group here. Now, as we're making our approach, remember, and before, I guess cheating the system actually didn't really help us here, because now I'm kind of going backwards. But remember, this is our original diene here, okay? And these three brothers are going to do exactly what they do best. They're going to rotate, all right? These three brothers are going to rotate. So let's erase them, and let's have them do their thing. One guy, and I'm just gonna straighten this, move this out just a little bit. One guy is gonna go here. One guy is gonna go here. One guy is gonna go here. Okay? This negative charge isn't here anymore. And that's the answer to this problem. That's the answer to this problem. Now, I know that was complicated, but hopefully, once you understand what's happening, and remember, this is what we drew within the first 30 seconds of this problem. We were so close to the answer, but we just had to figure out where a positive charge and a negative charge is going to go, and just in space, what is going to make sense. So if you keep all that in mind, you will definitely get this right.